party started. All right, so there is a homework assignment available. We'll have our usual problem session tomorrow. Next, I guess it's not next week, it's the week after. I'll be gone on, be traveling, so there won't be, just put it on your calendar, there won't be a lecture on the 16th of April. You can recover from doing your taxes. I know I'm now recovering. Anyway, but we'll talk about more the upcoming exam. There'll be one more problem set. The exam will cover time-dependent perturbation theory and tensor operators, okay? And also a piece of fine structure, hyperfine structure, which we'll revisit now, soon, to get you back in the group about thinking about that as well. All righty, so last time we made a very important connection between the properties of vectors and tensors in three-dimensional space and angular momentum in quantum mechanics. And that connection follows by noting that the three components of a vector with respect to the spherical basis look just like YLMs. And we know how YLMs transform. They are examples of angular momentum in quantum mechanics. Well, in this case, for L equals 1. All right? So, the important point here is that we can look at the properties of the so-called spherical basis, a basis for three-dimensional physical space, which has these components, okay? And those components are, those vectors are special because they are the eigenvectors of rotations in three-dimensional space around the z-axis by some angle, okay? So they are, that's why they're important vectors in three-dimensional space. We have one polar axis that we call the special axis, that's the quantization axis of quantum mechanics, all right? It's an orthonormal basis. Typically, we normalize them with respect to our inner product and complex vector spaces, and we can decompose any vector in three dimensions in terms of these through that kind of expansion, all right? And as I said, the key point is that the components of, first of all, say, position with respect to that basis, well, so x plus or minus I, y, or z, those have angular dependence that are the angular dependence of y L equals 1 with m equals q. All right? So they look like wave functions in quantum mechanics, I mean a function of space, three-dimensional space, for these components of angular momentum. And so we know how those components transform. Therefore, the three components of a vector in three-dimensional space, position vector, transform like the components of angular momentum. And that transformation matrix is the irrep of SU2, which is also an irrep of SO3 for the integers, for spin 1, j equals 1. Okay? So that's really the whole story, because everything builds from there. Because then we can look at generalizations of that. So now I can look at polynomials in x, y, and z, which are the polynomials that I get by you know, x, y, z, or r theta phi, it doesn't matter, because I mean, if I write this out, I could write this out, for example, let me just remind you, y2 plus or minus 2 is x plus or minus iy over root 2 to the power 2 with some constant up front. So it's a polynomial in x and y, in this case, which is also r to the power 2 times sine 2 theta, cos, etc. Okay? These polynomials in x, y, and z transform like angular momentum with magnitude L. So these polynomials, which we call the solid harmonics, transform like rotation matrices acting on the Hilbert space that is of dimension 2L plus 1. And that transformation is given by the irrep of that rotation matrix for that spin L. Okay? And I can generalize it even further. It doesn't matter what, if I plug in here instead of x, y, z, v sub x, v sub y, v sub z. So this would be v sub x plus or minus I, v sub y to the power 2. That transforms the same way. Okay? And we call these, and there are 2L plus 1 different such polynomials in the components of vx, vy, and vz. There are 2L plus 1 of them. We call them the 2L plus 1 components of a rank L irreducible tensor. Okay? So this, any 2L plus 1 objects which transform according to this rule are the 2L plus 1 components of a rank L irreducible tensor. Okay? So, what makes this irreducible? It's irreducible because it transforms according to an irreducible representation of the rotation group with that L. Okay? Now, as we discussed, not all tensors transform as some are reducible tensors. So, for example, we'll go back to what we discussed at the beginning of this unit. We talked about the dyadic. Okay? Dyadic is a tensor, but it's not an irreducible tensor. You can kind of see this because it has this kind of tensor product structure, right? And we can decompose it, though, into irreducible components. And as we discussed last time, there's a kind of rank 0, which is sometimes called the scalar component, which is just the trace of the matrix times the identity divided by 3, so that the trace of this is equal to the trace of that. Okay? There's a vector piece of this, which is an irreducible rank 1 component, and it's the anti-symmetric part of that reducible tensor, which was related basically, for the case of the dyadic, to the cross product between the two. And then there's a sort of irreducible tensor piece, which is the symmetric traceless part. And this is rank 0, so scalar is rank 0. It's like a spin 0 object. It has one component. This is rank 1. It's like a spin 1 object. It has 3 components. This is rank 2. It has 5 components. Yes?
Does the symmetric part, does it have to be traceless to be irreducible?
It does. I mean, because I can always break off the trace part of it, and without that, it won't transform according to this rule, which is what we mean by it. And another way of what I'm trying to say is that what we want to say that something is irreducible means that there are components that never mix with one another. So they're kind of blocks. And the trace is invariant under a rotation. So it is just a scalar, and it doesn't ever mix with this part. So we take it out. Okay, so one often talks about irreducible tensors as spherical irreducible tensors, but it's just, they are the components, the components of these, for example, irreducible tensors in the spherical basis. And you can kind of see that here. Suppose I write each of the vectors that were in the dyadic in the spherical basis. Okay? So this was, U tensor V. And now I'm writing each one of those vectors in the spherical basis. Well, this is the tensor product between those spherical basis vectors. But that's isomorphic to this, right? Because we said each one of these guys is like a L equals 1 with M equals Q. And we know, because we've been doing this, that if you look at the tensor product of two angular momenta, that can be reduced into the irreducible components through the Clebsch-Gordon coefficients. We would call these things the irreducible basis tensors. Yeah?
Just to make sure maybe I learned something from last homework, in that Clebsch-Gordon coefficient, the ket.
Yeah.
So is that like adding those two?
It's exactly what it is. So what I'm saying is this state in Hilbert space is equal to a superposition of different possible total angular momenta weighted by the Clebsch-Gordon coefficient associated with the addition of this to this total. Now, of course, it must be the case that Q, and one of these should be primes, that big Q is equal to little q plus little q prime. And in this case, what are the possible values of capital K?
0 to 2.
0, 1, or 2, right? Because when you add angular momentum, K is between L1 plus L2 and L1 minus L2, right? Magnitude. In this case, L1 and L2 are both 1, so the minimum value is 0, the maximum value is 2. So when I tensor together two vectors, I can get something which has the equivalent of total angular momentum 0, that's the scalar part, total angular momentum 1, that's the vector part, total angular momentum 2, that's the irreducible tensor part. Okay? But it's all really coming from the fact that these guys, x plus or minus psi, y, and z transform like L equals 1. That's where the structure grows from. All right, so then we took this and we talked about, okay, so these are tensors and polynomials of x, y, and z. And then we talked about tensor operators. So I could define, for example, a tensor operator where I took this function and substituted it, a position operator in there. And that transforms according to, if I look at the components of the tensor operator, rotated, so these are the rotated components. So these are irreducible tensor operators. So I'd rotate this. Look at the rotated guy. According to the unitary transformation, that this thing transforms just like the components of an irreducible tensor. If I leave the little arrows on top, if I'm talking about the components, excuse me, lots of, let's just forget it. Sorry. All right, so the components of the rotated tensor are related to the components of the unrotated tensor by exactly the transformation rule that we have over here for the solid harmonics. Right? It's exactly the same rule. And any object that transforms like this is known as an irreducible tensor, components of an irreducible tensor. Okay? And as we discussed, although we didn't just say that there's an infinitesimal version of this, that is to say, if T is a tensor, under rotations by J. So in other words, if for D generated by this angular momentum, if that is true, then you can rewrite this as that the commutator of Jz with each of the two k plus 1 components is this. And its commutation with J plus or minus is that. If it satisfies these commutation relations, then we say that T is an irreducible tensor under rotations generated by J. I'll explain what I mean more in a moment when I say a tensor under rotations by J. We'll re-emphasize what that means. So finally, last time, we said, although we didn't prove it, is that the important Wigner-Eckart theorem. And the Wigner-Eckart theorems told us that if T is a tensor, an irreducible tensor under rotation generated by J, and we looked at its matrix elements with respect to kets that are eigenstates in the standard basis by J. So it has eigenvalues J and M and whatever other eigenvalues we want to use to define the state. And we looked at that with respect to this. Okay, so this is, we're looking at the matrix element of one of the components of the irreducible tensor with respect to two states, which are eigenstates in the standard basis, then this was equal to, well, it's proportional to the Clegg-Gordon coefficient associated with adding angular momentum KQ to Jm and ending up with J prime n prime. And what's left over is independent of all the directions in space. It only depends on the magnitudes of things, and we call it the reduced matrix element. And this is the Clegg-Gordon coefficient. And that follows from, you can prove it, and it's a little tedious, so I'm not going to do it here. It's in the notes. It's also in textbooks. By just noting, if we consider this transforms like J prime M prime K that is to say, this object transforms under rotations like this. So I put them together and then I project, and that's where that comes from. Okay. So the key takeaway message here is that the two k plus 1 components of a irreducible tensor are like the two k plus 1 components of a spin k. It's like an object that carries total angular momentum k. And Q represents the projection of angular momentum along the quantization axis. Yes?
So, I'm up here at the door, you know, it's the tensor operators and it has, you know, the T sub Q, the K.
Yeah.
You're not, it's not to say that that's a solid harmonic, it just transforms like it.
No, I'm saying that's an example. Anything that transforms like that is called a tensor operator.
Okay.
Irreducible tensor operator, but this is just one example. I'm not saying everyone is this form.
Okay, thank you.
We will look at other examples. But these are examples. So for example, here's an example. If x hat, y hat, and z hat are the components, there's some constant out front. These are these are 5 operators, okay? They are 5 components of a rank 2 irreducible tensor operator, okay? These are x hat, y hat, and z hat are the 3 components of the position operator. If I rotated this around the z-axis, then z hat would go to z hat. X hat would go to x hat cos phi plus y hat sine phi, and y hat would go to y hat cos phi minus x hat sine phi. If I plug those into this, I will find that this goes to e to the plus or minus I 2 phi t plus 2 This goes to e to the plus or minus I1 phi, t2 plus or minus 1, and this will go back to itself. So what I'm saying is that this is one example where I rotated around the z-axis, that these 5 operators transform according to the rules of rotation.
So the superscript doesn't indicate rank, or does
It does.
It does indicate rank.
It does.
Okay, so I just need to, okay.
So what's the confusion about that?
Well,
This is a rank 2 tensor,
Uh-huh.
which means it has 2 times 2 plus 1 components. Here they are, 1, 2, 3, 4, 5 components.
Okay.
So these are the 5 components of a rank 2 irreducible. And you also see the rank 2 because they're polynomials of order 2,
Okay.
right?
And
Yeah.
going back to J, so J is the total,
I'm not saying what J is yet.
okay.
I'm saying J is a thing that generates rotations of some kind, and I'm not telling you what it is. So you shouldn't even know. It just transforms this way, and we will see. Okay? So in this case, J was L. Okay? J was the actual R cross P. That was what J was. And because it's the thing, so it is the thing that generates a rotation. Now let me ask you a question here. Suppose I let J be this. So it is orbital and spin. Are these 5 components, are they a tensor under generation of rotations according to J? They're certainly rotations under L, but are they rotations under J?
If you tensor everything to the identity, so it's on the same space.
Yeah, it is. Because this does nothing to it. So it's also a tensor under this. Is it a tensor under this? Where this is the nuclear spin? Absolutely. So it's a tensor under L. It's a tensor under J. It's a tensor under F. We'll come back to that. That will be important. Yeah.
But then it's not a tensor under S alone.
It is not. It is not. Nor I alone. All right. Very good. So, let's look at an important example. So let's look at the interaction of an atom with one valence electron and the electromagnetic field. Okay? So, well, generally, we said that we can write the interaction Hamiltonian of this if we have in the multipole expansion, when the size of the atom is small compared to the scale over which the field is changing, as in a electromagnetic wave, which wavelength is long compared to the size of the atom. Then we wrote that the interaction we have the electric dipole times the electric field at the position of the atom function of time. And then we have the magnetic dipole dotted into, and we have, for example, the quadrupole, electric quadrupole. Okay, and this is an operator. So, what we have in the multipole expansion is that the lowest order multipole dominates. Okay, so this is the dominant interaction. R here is the center of mass position of the atom. Okay. E and D are classical fields. Yeah.
But isn't mu dot B the lowest order magnetic term?
Well, if this is non-zero, this will dominate over that. Okay? Let's remind ourselves why. If I have a charge, some charge distribution, and I shine a field on it, the dominant interaction is electric dipole. There will be some magnetic dipole interaction with it, but it will be tiny under whatever the small expansion parameter is, which we'll remind ourselves of if you haven't thought about that in a little while. All right, so this is the dominant effect in the multiple expansion. So let's look at this for the case of a plane wave. So my electric field is the real part of some polarization at some amplitude e to the I, the k of, I'll call it k of the laser, dotted into the position of the atom, e to the minus I omega. Okay. So that's the most general form of a monochromatic, it's a plane wave that's monochromatic. With frequency of the light, omega, right? Let me, although it really doesn't make a difference, it's just less notation carried around. Let me take atom at the origin. The atom moves around and gets complicated. Let's just fix it at the origin. Okay? So this then is equal to a half this plus its complex conjugate. Okay? This could have a phase. That complex if I like. All right? So, my interaction Hamiltonian in the electric dipole approximation which in this case, if I have a plane wave, means that the wavelength of the light is huge compared to the size of the atom. Is that a good approximation? Depends what the wavelength is. But unless I'm talking about gamma rays hitting my atom, this is a half of an angstrom, maybe hard X-rays. This is an excellent approximation, right? All right, so my interaction Hamiltonian then is minus d minus a half the dipole operator dotted into epsilon, the polarization, E0, e to the minus I omega t, minus a half d dot epsilon star, E0, e to the plus of I omega t. Okay. This is what we have called, we have a harmonic driving of the field, what we call the positive frequency component of the interaction. And this is what we call the negative frequency part of the interaction. Okay? And as we saw in perturbation theory, this is the thing that drives absorption, and this is the thing that drives emission. Okay? So what we have, for example, in Fermi's golden rule is that the rate of absorption from some ground state to some excited state is proportional to the matrix element of the positive frequency component of this squared. Right? So that is equal to, it goes like proportional to the matrix element of the dipole operator along the direction of the polarization squared, times electric field squared, which is, intensity. But it's proportional to this, right? So the rate of absorption depends on the magnitude squared of the dipole matrix element along the direction of the polarization. Okay? So now let's look at, so the question is, what are my ground and excited states here? Okay? So let's generically say that the grounds, that this state has some good quantum numbers. It's got some ground state quantum numbers, but it's also got some total angular momentum J and some projection M. I'm not telling you yet what J and M are, but let's say that it's good eigenstates of J and M. And this has some J prime and M prime. For example, if I ignored spin altogether, if I can do that for some reason, this could be L and M sub L, and L prime and M sub L prime. Or if I include the fine structure, this could be the total electron angular momentum, J and MJ. Or if I included hyperfine structure, then this would be F and M sub F, and M sub F and F prime and M sub F prime. Okay. All right. So now D, of course, is the charge of the electron, or the single electron. This is my dipole operator. Now, this is a vector under rotations. Generated by L or J or F. Any one of them. It's a vector under rotations generated by that, for the very reason that we just described. Okay? Is that clear? So, what that means is that the components dq are components of a rank 1 irreducible tensor. It's rank 1. Its vector is rank 1 tensor. And with respect to the spherical basis, these are the components. Okay? So, what that means is that my absorption less coefficient is equal to, so D is sum over Q dq dq star. Right? Because when I dot it, I get dq. So let's plug that in. Just looking at the projection, I just haven't plugged in that. I guess that sum should be inside. Yeah. Absolutely. So the absorption coefficient is proportional to this. Less right. So what do we see here? Well, we have the Wigner-Eckart theorem. This is a rank 1 irreducible tensor operator. So according to the Wigner-Eckart theorem, this is proportional to a Clapeyron coefficient. This squared is, I'm sorry, right there. Clapeyron coefficient associated with the addition of angular momentum, rank 1, projection Q, J, N. And then there is a reduced matrix element that only depends on the magnitudes of things. So, what can we see from this? Well, one thing we see is that from this we have selection rules. This matrix element will vanish unless the following is true. It must be the case that M prime is M plus Q. And that selection rule is generally Q can be either 0, plus 1, or minus 1. So we cannot change M with an electric dipole by more than 1. We can keep it the same, or we can make it go up or down by 1 value. Moreover, J prime here can, according to this selection rule, is equal to j, it could be equal to j, it could be j plus 1, or it could be j minus 1. Now we'll see in a moment that actually this is actually not allowed. Not apparently, but we'll come back to that. But by angular momentum, it would be fine. There's no reason angular momentum could be conserved. I could make, because when you add one unit, right, j prime is between j minus 1 and j plus 1. Right? So that's what angular momentum tells us is allowed. All right, so what about which value of q? Well, that depends on what the direction of oscillation is of the electric field. With respect to this component. So, the direction of polarization determines the components E sub q. Right? So, for example, so we have a, so this, I want to emphasize some points here because I find it's always confusing.
Is that the vector or direction?
It's a direction. So we have an axis, so we have our spherical basis. Okay. E0 is the z-axis. E plus or minus 1 is x, ex plus or minus iy. All right? So, we have some coordinate system we're calling x, y, and z. Okay? And we have defined our standard basis with respect to the special axis we're calling z. We can call z anything we like. We can impose any coordinate system on the world we want to describe the world, even if the world doesn't know what we're calling the z-axis. But we call something the z-axis and something the x and y-axis, right? So this corresponds, let's call this the z-axis. If my polarization were along this, that would correspond to linear polarization along the z-axis. So if epsilon is along this axis, then it's oscillating linearly along z. If it's doing this, then it's oscillating either with right or left-handed helicity with respect to the z-axis. So this would correspond to E plus, this is the z-axis, and this would correspond to E minus with respect to the z-axis. Now note, I've said nothing of the direction of k. I didn't say whether k is along z, x, or y. Obviously, if k is along z, I can't have this. I only have these guys. If k is along x, well, I can have this. I can have, if it's, if k is along the x direction, I can have a piece of this, right? The piece that's oscillating out. It would be a linear combination of this and this. If it's propagating along z, I can have this and this, but not that. So the directions of oscillate, I mean, the atom's sitting there and it's feeling, you know, the polarization going, but it doesn't know where it came from. It just feels locally at its body, whether it's rotating around, going up and down. It doesn't know what the propagation direction is. So the propagation direction has nothing to do with whether we call, you know, what we could call, we can choose to call the z-axis the propagation direction or not. It's up to us, okay? And so remember, z here defines what we're calling the quantization axis. Of the atom. The basis that defines what we call M. Okay? If the polarization is along the quantization axis, if it's parallel to the quantization axis, then in German we call it pi. And if it's perpendicular to the, so this is parallel to z. If it's perpendicular to z, we call it sigma. And there's two possibilities. It could be sigma plus or sigma minus, because sigma is the German for perpendicular. So sigma plus and sigma minus, as we will see, have to do with the component relative to z, not the component relative to k, necessarily. Okay, so what that means is the following. Let's imagine, let's consider my ground state is the 1s state of hydrogen. And my excited state is the 2p state. Okay? With a given value ml being +1, -1, or 0. Let me ignore spin. Then this is my ground state. L equals 0, ml equals 0. This is my excited state. It's as L equals 1, ml -1, 0, or +1. Okay? All these transitions are allowed because they all satisfy my selection rules. Okay? L changes by 1. M sub L can change by +1. It can stay the same, or it can change by -1. Right? This would be the transition that would be driven if I shine pi light on the atom. This would be the transition that would be driven if I drive the atom with sigma plus. And this is the transition that is driven if I drive with sigma minus. Of course, what the Wigner-Eckart theorem is telling us is about the conservation of angular momentum. So the reason I went from an atom that had no projection of angular momentum to 1 unit of projection is that it got it from the photon. So these helicity, this is the helicity of the photon corresponds to the spin projection of angular momentum of the photon. The photon is a spin 1 object because it's the quantization of the electric field, which is a vector, which is a rank 1 tensor, which transforms like a spin 1. And it has projections along this axis of +1 or -1. Now, of course, the helicity of the photon is relative to its direction of propagation. So if I have k here, The helicity of the photon represents the amount of angular momentum it has along K. That's what we call the helicity. Is the spin projection along K. And that can be +1 or -1. It can never be 0 along K. But it could be 0 respect to something else. Right? I can have 0. Of course, this is a superposition of this and this. Okay. All right. Suppose I now include the fine structure. Okay? So now the ground state of hydrogen is what? Well, I have the spin of the electron, and I couple spin 1/2 to L to get total J, right? What about the ground state? What are the possible values of J?
Just J equals 1/2.
It says J equals 1/2, right? Because L equals 0, and we have the it's the 1s 1/2, right? But it has two sublevels corresponding to spin up and spin down. This is Mj is -1/2 and Mj is +1/2. Okay? Then I can have, for example, for the 2p, I can have a 2p 3/2 and a 2p 1/2, split by the fine structure splitting in hydrogen, right? And that has Mj values -3/2, -1/2, +1/2, +3/2, -1/2, +1/2, etc. Okay. So now let's look at the selection rules and allow transitions. Okay? So let's consider my ground state being the 1s 1/2. This has ML or MJ equals ±1/2, right? So this is my ground, possible ground states. My excited state, 2p, let's say the 2p 3/2. My dipole matrix element here that I care about is this for a given component along Q. All right? This is a vector, so this is a vector under rotations generated by J. For the reason we described before. So the Wigner-Eckart theorem applies. There's the reduced dipole matrix element and the Clebsch-Gordon coefficient. Doodly-doo-doo-doo. This should be 3/2, probably. That's what I'm looking at. So now you tell me, what is the Clebsch-Gordon coefficient? What's the total angular momentum of the final state?
3/2.
3/2, with projection mj prime. Right? That's this state. And I start in a state which has what angular momentum?
1/2.
1/2, thank you, with projection mj. And I add to it what? It's a vector, 1 unit with projection q. So the Clebsch-Gordon coefficients, so in this case, again, mj prime has to equal mj plus q. Okay? So if I start here, what are the allowed possible final states I can drive?
3/2.
Depends on Q, no?
Right? I can go here, here, or here if I have sigma plus, pi, or sigma minus. And what about here? This is, I can't do that. Ixnay with the change by 2 way. Right? And if I do here, I can do this, or this, or this. If I have pi, sigma plus, or sigma minus. Okay? The amplitude, or the probability of doing it, the rate of doing that depends on the square of the matrix element, which depends on the square of the Clebsch-Gordon coefficient. Okay? So the rate of absorption of this, the rate of absorption, if I have a pure Q, depends on the square of this guy. So the square of the Clebsch-Gordon coefficient tells me the rate of absorption for this. So, and I know these guys because this is a famous word in quantum physics. This Clebsch-Gordon coefficient is 1. This square Clebsch-Gordon coefficient is the square root of 2 over 3. This one is the square root of 2 over 3. This one is 1, and the middle guys are the square root of 1 over 3.
And that's including the prefactor of the reduced.
That's just the Clebsch-Gordon coefficient. The reduced dipole matrix element depends on the details of the radial wave function. Okay? So you have to calculate that radial overlap.
So these numbers are kind of a
These are they are the kind of universal for S to P. No matter what this prefactor was, it would all be this for a S1/2 to P 3/2 transition. Yeah.
Is because the coefficients have to always be equal to 1, it's a square term, so they're equal to 1. Is the parallel component always equal to 1?
Yes. I mean, so what you're noticing is an important point, and this is something you'll see in your homework. What must be the case is that the squares of, so the total decay rate, if I were to start something here, it ends up here. If it starts here, it ends up there. If it comes up here, it can end up there. But the total rate of decay can't depend on what direction the atom is pointing in. Because how the hell does the vacuum know? I mean, how the heck does the vacuum know what direction the atom is pointing in?
It flips a coin.
It can't know. So it's got to be that this is equal to the sum of this plus this is equal to the sum of this plus this. So if this is 1, it's only one way, then this is 1/3 plus 2/3, etc. That's a rule. All right. So
If you move from the 2 to the 3 stage, you have 5 different choices in which to go, right?
the 2 to the 3 stage.
Like you can go from like 2s to 3p.
The principal quantum number does not affect the number, the degeneracy. That depends on the total angular momentum, J or F. So it has nothing to do with whether it's 1p, 2p, 3p, 100p. I'd have the same number depending on J, or F if I include nuclear spin. Okay, now I want to emphasize one point here. The choice of quantization axis is arbitrary. So let's consider the case of a linearly polarized plane wave. Okay? So here's the direction of propagation, and here's the polarization direction. Okay? I can call X, Y, or Z anything I like. All right? And it can't matter what I call X, Y, or Z. So if I choose the Z-axis like this, then this is pure pi polarization. Right? If I choose the quantization axis like this, then what would you say about epsilon? Well, it's pure sigma, because it's purely perpendicular. Sigma means perpendicular to the quantization axis. And this is, of course, a superposition. In this case, epsilon would be, if I call this, say, the x-axis, is E sub x, right? But E sub x is a linear combination of E plus and E minus. So this is a superposition of both polarizations. It is a superposition of left and right circularly polarized light. It must be the case that the rate of absorption that I get is independent of that choice, right? So let's prove that. Let's show that it does not matter what I choose. There might be a more convenient choice, but at the end of the day, physics can't depend on the coordinate system that I impose to describe the physics, okay? So let's, of course, I have to think about the state as well, what my initial state is. So let's say that my initial state, let's come over to this board. So let's say that my state, let's say that it has projection nj equals plus 1/2 along k. So I prepared the state by the process of optical pumping. I polarized the atom to have maximum projection, so in the ground state, along this. Okay? So that's the state. Now I'm going to put a coordinate system. So let's look at case 1. So the state is this, and the light is linearly polarized. Okay? So case 1. Let the z-axis be along k. No, along epsilon. Okay? Now let's do the other one first. Let's do the other one first. Let's say it's along k. All right? So my state, in this case, the grounds initially, is what? It's the 1s 1/2 with nj, okay? Because this has 1 unit of angular momentum along the z-axis. Okay? All right, so I prepared the state here, and now I'm driving the system with linearly polarized light. But my linearly polarized light is a superposition like this. My dipole, so epsilon is minus this plus this over root 2, right? So d dot epsilon is minus 1 over root 2 d plus 1, no, plus 1 over root 2 d minus 1. So what transition do I drive? I drive the atom into a linear superposition. The atom starts here, and it is in a superposition of these two states, because there's a coherence here. So it becomes a superposition of these two states. Okay? Now what is the rate of transition here? Well, the rate of transition is proportional to this, right? And that is equal to, well, a half of the intensity, because I square that, goes from this to the excited state with this excited state with D plus.
Should the sum be under the same absolute square?
It should, but it doesn't matter because only the selection rules only pick off one. Okay? In other words, let's write it out in more detail. There's a D plus 1. It can only drive this transition. There's a D minus 1. It can only drive this transition. And according to the selection, to the Clebsch-Gordan coefficients, this would be equal to,
I think that's root 2, not root 1.
it's No, it's,
yeah, right, I was reading the diagram wrong.
sorry, it's root 3. This is 1, and this is a third, up to the, just saying, forgetting about the reduced dipole matrix, up to 1, not, and 1/3, right? So the total of this is 2/3. Okay, because these are the two transitions. Now let's do it the other way around. Let's say that I drive, so in this case, case 2, I'm going to choose the z-axis along epsilon.
Just a quick question.
Yeah.
I'm sorry, does this mean that there would be 1/3 of a chance to find it in one state and more of a chance to find it in the other state, or no?
Absolutely, absolutely. So this, what is produced here, suppose I Rabi oscillate.
Okay.
If I Rabi oscillate, what I'll find is that if I did a pi pulse, the atom would be in a linear superposition of a quantum superposition of this state and this state. It would be 3 times more likely to find it here than here. Who cares? It just means that that state, the state that's produced by that addition of angular momentum, is not an eigenstate of angular momentum along the z-axis. Because it has a linear combination of helicities, it's not an eigenstate of helicity. It is a superposition of helicities. And because it is a superposition of helicities, there are 2 elementary processes, and the atom ends up in a superposition state. But any superposition state is another man's eigenstate. Let me explain. So I want to conclude, because I wanted to talk about this last case, and put the full logic together. So let us look at this case too, where this is along this, which is the x-axis. Okay? Now my state, my initial state is what? Well, it's still the same state, but with respect to this coordinate system, it's no longer an eigenstate, right? It was spin, maximum spin projection along this axis. Which means that, so this state, I'm sorry, I'm going to call this the z-axis. This is the z-axis along epsilon. So the k-axis is the x-axis. So this is spin up along x, which is a linear combination of spin up along z and spin down along z. Right? So the atom starts in this superposition state. But, you know, it's just in a different basis. It's the same state. This is spin up along z and spin down along z. Right? I drive the system with linear polarization along z. Which transitions do I drive?
1/2 to 1/2, maybe 1/2 to 1/2.
Exactly, the pi transitions. Okay? Of course, what that means is this superposition becomes this superposition. But of course, that must be the case. That's just a change of basis. This state is this state. It's just this is with respect to a different axis. It's just a different basis. Okay? Let's calculate the, and this has square root of 2/3, square root of 2/3 as the Clebsch-Gordon coefficient. So if I look again at this d dot, right? And this is d0. I'm going to square it. I have a half of this transition, a half of 2/3, plus a half of 2/3, which is again 2/3. So it's the same thing, it's just with respect to two different axes. So I just want to conclude with one final statement. It's often stated, this is the transition for linear polarization, and this is the transition for circular polarization. That's BS. That's wrong thinking. Hasn't had anything to do with whether it's linear or circular with respect to K. It's linear or circular with respect to what I'm calling the quantization x of the atom. They might align. If this case they did, I put the quantization x along epsilon, then, or it might not. This was linear polarization. But linear polarization was a combination of sigma plus and sigma minus. It's up to you to decide what's convenient for your problem. All right, lots to absorb. We will finish our discussion of selection rules and multipolar moments next time.